Okay, our next speakers are Mirjam Kirchner and Lin Ao from DigiQ, and they will tell us something about using geospatial data to solve Germany's heat transition problem. So please go ahead.
Thank you very much for the warm introduction. As already being said, my name is Mirjam. This is Lin. Lin is from Data Insights, who is supporting us at DigiQ. And in this talk, we're going to talk about how to use geospatial data to solve Germany's heat transition problem. As the probability is high that you already know what DigiQ does by now, I'm going to skip through the introductory slides a little bit. If you have any questions later on, just feel free to approach us. So at DigiQ, we are a German startup that is active in the energy sector, and we developed a digital twin for the German heat supply at the building level. And we are currently focusing on the heating sector because it is responsible for a large portion of the greenhouse gas emissions in Germany. So in 2020, that was 40%. And to get this not the percentage down, but the overall emissions down, German lawmakers recently passed a law that that obliges the municipalities, and we have 11,000 of them, that they must come up with a heating concept or strategy how to reduce these greenhouse gas emissions in the heating sector. And when you derive such a heating concept, you might ask many questions, but in this very talk, we're going to focus on where infrastructure providers should actually build new district heating networks or expand existing ones. And we're going to answer these questions in 2 steps today, not 3 like yesterday. So Lin's going to start with the question where to actually focus, on which areas you actually should focus to build a new district heating network. And I'm going to then build on it and evaluate whether that building in that area is actually worth it. And without further ado, I'm handing over to Lin.
All right. Thank you, Mirjam, for the great introduction. So let's talk about district heating a little bit. So for those of you who might not be familiar, district heating is just another way of how to get heat into your homes. So compared to like a local heat production method where you might have a boiler in the basement of your building, which is using fossil fuel or gas to produce the heat that's needed for the building, but only the building itself. In a district heating network, you usually have at least one large centralized heat production facility that is producing heat, the necessary heat for the entire network. So the heat is produced at the centralized location and then transported to the individual homes through a series of pipes. And obviously this needs a lot of infrastructure. The advantage of district heating is you have a greater control of what sort of energy sources are being used to produce the heat that supplies your municipality. As you can imagine, district heating has some great benefits from economies of scale. So the larger your network, because within the district heating network, you have this large fixed investment cost, which is the heat production facility if you don't have one already. And the larger your network, the lower the average cost of this heating facility becomes. And so the lower the cost of the average heat demand that is being satisfied by your network becomes. So if that was the only constraint, of course, you would want to build your network to be as large as possible, to supply as many homes as possible. But unfortunately, building the pipelines itself also costs money. So there is a certain trade-off, there's a certain financial trade-off of building infrastructure and how much value you actually get out of building this additional segment of infrastructure. And that is sort of the core problem behind the question that we want to answer, which is where do we actually want to place these networks? And to what extent? Because up to a certain size, or from a certain size on, maybe the network does not become financially viable because not many people are going to benefit more from this additional network that you're building. So let's take a look at first what we would like to do and we don't want to do. So with our approach, we don't want to provide exact forecast. And what I mean with that is not that we don't calculate any exact numbers, but rather that we don't do it on a individual building level. Because as you can imagine, for the heat planner who's working with this and who's planning the district heating network, the importance of whether or not this specific building is attached to the network is not as important as this whole aggregated value. So for each segment for each segment of pipeline that's being laid, the heat planner wants to know how much heat demand is being satisfied by this from the surrounding area. It doesn't really matter where this heat is being used from, but rather just this overall aggregated value that's important. The second thing we don't want to do is we don't want to have a fixed solution that is sort of applicable or applied to every single municipality, because there are a lot of variances, local variances, because due to maybe policies or maybe like geographical features and maybe other factors that plays into this. So for every municipality, for every project that we work on, we need to be able to adjust the constraints we set, to adjust the parameters, to adjust what sort of things that are important for the considerations. And finally, we don't want our results to make decisions in itself, but rather these are supposed to provide as much information as possible to human experts who then will use this information and make their further plannings with it. So as for the overall approach, it's very simple, basically. We start with this digital heat map, which is this building data set that we have, which includes, as you've heard before, structural data regarding the building, how tall it is, and then how much heat is necessary to satisfy the heat demand of this building, and also some socio-economic factors. And based on this data set, we can then identify areas of high district heating potential. So usually the three common factors that we have in every project, which is like main factors, of course, the heat density. So you want to have an area with high concentrated heat demand so that you can build a small network which then satisfies a lot of heat demand all at once. But also the number of buildings and the number of households will play a role into this consideration, because you don't want to really build a network just for, in the extreme example, just for one single building, even though that building might consume a lot of heat, because it's hard to justify that sort of investment just for one single building. And from there on, we can form these networks and do some classifications about the types of networks we have, whether or not there's already district heating available, whether or not you can consolidate the district heating like sort of density within the network, whether or not you can expand the network, or whether or not you need to construct entirely new networks because there might not be anything existing. As for the implementation, I'm just going to show you some brief examples of how that might look like. So what we start with is this large buildings data set. This is for the German city of Essen, where Digico is located at. So having data available on the building level is great, but that's, as I said, that's not the sort of the scope that we're interested in. We're more interested in this aggregated view. And for that reason, we first aggregate all the data available to sort of hexagon shapes. So we chose hexagon because it's very easy to fill any sort of form and shape of any municipality with hexagons without having a lot of waste. And those hexagons can also do a better job at representing the actual shapes of the networks, because using squares, you only have two axes available, and this gives you an extra dimension to work with. And also, I think just hexagons are more visually appealing than squares. And from there on, for example, you can first identify the existing district heating infrastructure. So this can be done using building level data. If we see that the building is already heating with district heating, then we assume obviously in that grid, in that hexagon, there's already infrastructure available. Or if you actually have the actual shapes of the district heating infrastructure, then we can project that onto the map as well. Out of the surrounding areas, or out of the remaining areas in gray, these are all candidates for district heating potential. So based on certain KPIs that I've mentioned before, such as the heat density or the number of buildings within the hexagon, you can identify some areas where the potential exists for district heating. So this is just an example based on 3 simple criteria that I mentioned before. In reality, you might consider a lot more factors. So as we can see, because Essen is a somewhat large city, there is obviously potential everywhere because there are a lot of people living there. So the next step would then to be just formulate these networks. And out of those networks, so each of these would be a candidate as a potential district heating network that you can construct. There is actually additional steps that we need to do to fine-tuning the shapes of these networks, because what we've done so far is just combining all the hexagons that are touching each other in order to form these forms. You might have the case where you have 2 networks which are located very closely to one another, but there's like some sort of empty area in between. So the density in that area is not as high. So if you consider that hexagon on its own, there is no potential for district heating, and that will not show up in the sort of the potential map. But in reality, the obvious thing to do is just to build infrastructure anyway, because it's a lot cheaper to have one large network than 2 separate ones, because you would need 2 heat production facilities. In order to identify this problem, we just sort of kind of have to find these networks that are located closely to one another, and then compute a sort of a shortest path through this hexagonal grid in order to combine these networks that in reality you would actually make into one. So all of this obviously is made possible with these great open source libraries, GeoPandas and Shapely we use for these geospatial computations, and also the H3 library for creating this hexagonal grid. Now I've showed you the example of a very simple case of identifying these networks with 3 simple criteria. But in reality, the problem is a lot more complicated. There are so many different factors you have to consider. So sort of optimizations to how you would identify these networks would be using human expert knowledge to set different KPIs, not just based on heat density, based on number of buildings, but other things. You have regulations that you need to consider. Where are you allowed to build? Where you are not allowed to build? You might have some financial incentives from local governments to construct in a certain area, but also other sources of information such as renewable potentials. Where do you have high solar potential, wind potential, hydro potential, or geothermal potential? Now, these things obviously can be beneficial to a district heating network because you can use these renewable energies to produce the heat, which obviously makes your entire network carbon neutral. But they also can be competitors to district heating, because if you have an area with high solar potential, then the trade-off for each building would be, do I install solar panels on my roof, or do I use the district heating network? So there's these sort of issues to consider as well. And also existing infrastructure is also a factor. If you have an industrial area nearby where heat is already being produced as an industrial byproduct from their manufacturing processes, then that heat can be used to heat up, to generate the heat for the network. That saves you a lot of money as well. The layouts of the streets or some natural boundaries will determine how the shapes of your network will be. But also sort of, especially in city centers, you might have areas that are under, that have some sort of cultural heritage that are under monumental protection, where it's not as easy to do large construction works. So all of these factors, and these factors differ from project to project because, yeah, every city is different. And out of this, we get these candidate networks, a few of them that we can do further analysis on. And I'm going to hand over to my colleague, Mirjam, for that.
Thanks very much. So now that we have these potential areas, we're going to look at the question whether it's worth it or not. And there might be various different stakeholders who have an interest in that. So these pictures are AI generated using the prompts in the boxes. So on the right-hand side, you have homeowners who have to decide on the technology that they want to use to heat their homes. Then in the middle, you have a politician who wants to build a sustainable community. And on the very left-hand side, you have the investor who actually builds the network. And in this, like all of these are important stakeholders when it comes to the heating concepts that a municipality derives. But in this very talk, we're going to just focus on the investor. So we focus on the sole economic perspective. And when it comes to investments, actually the capitalized value is a standard measure to evaluate whether making an investment is worth it or not. And I don't want to go into the very details of the formula, but what's important to know is that the capitalized value actually, let me check whether I have, the capitalized value actually looks at the bigger time frame, so over multiple years. And the typical lifetime of a heating district network is 20 years. So we're going to look at all of those 20 years when we compute the capitalized value, and then look at the total cash flow that is generated by the district heating network every year. And the way you can think of the capitalized value is actually the monetary value that the district heating network has to the investor today. So if the capitalized value of your investment is above zero, then it's worth something to you or to the investor. But if it's zero or below, then the investment is not interesting for you. And you can also use the capitalized value to compare different investments. But in this very use case, we're just going to look at this one district heating network and whether we want to build it or not. So now that we understand what the capitalized value is, we can actually reformulate the original question that we had and make it a bit more specific. And we can reformulate it and say, can the investor actually build a district heating network with positive capitalized value? And if that is the case, then they might consider building it, depending on whether they have other investments that are interesting to them. And we're going to look at this question using the example of Böen. I want to give you a little bit of geographical context. So this red blob here, that is Leipzig in the east of Germany. And then just south of Leipzig, there's Böen. And here you can see the results for Böen of the analysis that Lin presented just in the first part of this talk. And we chose Böen as an example, or as a first step, as a proof of concept, because it has a manageable size of potential district heating areas. And it also has an excess heat source nearby. So in the southeast of Böen, there's actually an industrial area with excess heat that you could use to connect all of these high potential areas with, and then build your district heating network. And for the sake of simplicity of this talk, we're not going to look at all the different cash flows that the capitalized value of a heating district has. We're only going to look at the heating income as a cash flow and the pipe investments. So the heating income is just the money that the investor makes by selling heat to the customers that are connected to the district heating network. And the pipe investments is the money that the investor needs to spend to actually build the network. So depending on how much heat the investor decides to sell or which pipeline they want to build, they can actually, or by making these decisions, they can actually manipulate this capitalized value depending on how they decide. And in the real world, the investor, or we're going to start with looking at the pipe investments a little bit more closely. And in the real world, we actually have to decide for every single house in Böen whether we want to connect it to the district heating network, yes or no. But to come back to what Lin said initially, it's not our intention to design the perfect district heating network for Böen. We just want to evaluate the investment decision, whether it's worth it to build the network there, yes or no. So in order to ease the problem complexity, we're not going to look at all the individual households. We're just going to decide Do we want to connect one of these high potential areas with the heat source in the bottom left corner, or do we not want to connect it? And by doing this, we actually reduce the complexity of this problem quite a bit. In the case of Böhlen, it was from like more than 14,000 decisions that the investor needs to make to like just 180. So it's worth making that simplification for our use case. And still, we now want to construct a solution space of decisions that the investor can make to actually build the network. And if you look at all of these high potential areas, then there are like actually infinitely many ways how you could connect one of these potential areas with the heating source. So I could go up way to Leipzig, build a pipe there, and then go way down. But of course, from an economic perspective, that just doesn't make any sense. So we wanted to construct a feasible solution space for the decisions that the investor actually would make. And we did that by constructing a complete graph between the high potential areas and the heating source. So in a complete graph, every node is directly connected with any of the other nodes in the graph. And when it comes to the municipality of Böhlen, we just took the centroids of each high potential area and then computed the shortest path along the streets in Böhlen to construct an edge between these two nodes. And if we do that with all of the high potential areas in Böhlen and the heat source, because that's where we want to connect to, then you get the solution space of decisions, of reasonable decisions that the investor has. And now we can start, we can try to optimize this by making or modeling the decisions, building the pipeline, yes or no, and then seeing what happens with the capitalized value. And just as an FYI, we constructed the solution space using the packages OSMNX and networks. Okay, so that was the pipe investments. Now we're going to look at the other decision that the investor needs to make. How much heat do they actually want to sell to their customers? And of course, from an investor's perspective, I want to sell as much as I can. But we have to keep in mind that when it comes to the heating income, that will always be constrained. So it's limited. And there are three reasons for that. The first one is fairly obvious. So here we have the heating source, and in order to sell heat to this area, I need to have made the decision that I actually built the pipeline and connected it to my source. So that's a limitation. The other one is that my supply actually can never exceed the demand that I have. So every high potential area that Lin created has a limited amount in every investment period, and I cannot sell more heat to this area than even if I wanted to. And lastly, because we are in the renewable energy transition, it might be the case that we have an industrial area, and that industrial area has excess heat, but then it doesn't make sense for that industrial area to produce more heat than they actually do by the regular processes. So I cannot sell more heat than my heat source provides or may provide. And if we now piece everything together that we learned on the previous slides, we can actually construct an optimization problem. So on the left-hand side, you see the standard structure that a mathematical optimization problem has. So the function f of x is called the objective function that typically is minimized. In our case, the objective is that we want to maximize the capitalized value by making the decisions, that is, the decisions is the variable x, by building pipes and supplying heat, and then scaling this function up and down, or making it as large as possible. And we have to do that by still complying with the constraints that I previously talked about. So we still have to consider that we can only send heat to a certain area if the pipeline is built. We cannot sell more heat than is demanded, and we can also not supply more heat than is available. And I assume that some of you are familiar with this formulation, but for those who are new to this formulation, I really like this picture. So by formulating the problem that we have this way, we are actually creating a solution space that there is this, this brownish area here. And as long as we make decisions that keeps us within these boundaries, they are feasible. But as soon as I leave this area, then I'm actually starting to make decisions that are infeasible for my problem. So that would be sending heat through a pipeline that doesn't exist. Then I'm outside of the scope. And then actually my objective function is then like a compass to navigate through this space. So it gives me direction where I need to go to maximize or achieve the goal that I actually have. So in this case, this is indicated by this arrow. So if I am in this space, I just have to further go in this direction, and my objective function will improve and improve and improve until it can't improve anymore. And luckily, once we have this form, we can just throw a standard algorithm on it. So there are like multiple solvers available. We use the library AMPL, and from that library the Higgs solver. And we use Pyomo to formulate the problem at hand so that we can then just solve it with AMPL, just in case you want to do this at home. And looking at the time, yeah, we still have time for results. So these are some resulting plots that you could generate with our approach, which currently has POC status. So once you have the optimal solution for this optimization problem, you know which pipeline the investor should build. So in this case, of all the different, like remember this messy plot with all the different connections between all of the high potential areas. Of all of these pipes, only like 2 of them are being built, connecting the heat source with the largest high potential area. What we also get, because recall that the capitalized value is an aggregate statistic over the entire investment period. We also know when the investor makes the decision to build the pipeline. So here the single dots are the high potential areas. And we can see the decision when it's optimal to connect the heat source with a certain high potential area. And lastly, the plot on the right-hand side, the gray slope here, that is the capitalized value over the investment period. And you can see that in time period or investment period 11, we break even. So moving onwards from that point in time, the investment actually becomes positive, so profitable for the investor. And all of the different colored bars are the different types of cash flows that we have to consider to calculate the capitalized value for the district heating network. So we also know which cash flows are the cost drivers, and also, well, we only have heating income, frankly, as positive, so that is the only green bar, but we have the different cost distribution of all the different cost drivers as well. There are, of course, limitations to this approach. So one could argue that the economic perspective that we take is just too simplistic. Also that one might be more interested in going down at the building level, but we see that as a different type of problem that should be further analyzed once you already know that you should look into this area a bit more closely. And lastly, with the optimization problem approach that we took, we only get the best solution to this problem. So we don't get the second best or the third best, we only get the very best. So if you want to explore your options a bit more, you have to tweak the optimization problem, for example, by fixing certain decision variables. For example, it might be that you have local knowledge and know I'm always going to build this pipeline, so I'm fixing this decision variable to 1 and say this pipeline is always being built, and then you recompute or re-optimize the model, and then you can explore the solution space a bit more and can get suboptimal solutions. but that's the only way in this regard. So that might be a downside. Then lastly, possible extensions. So we could add investment constraints. So it might be that we don't have an infinite amount of money available at any point in time. Currently, we assume that, which might not be reasonable. Also, we assume that every pipeline is being built in just one time period. And it might be that particularly for longer pipes, we might need more than a year to build a pipe. So that might be an extension. And we also currently, like, a little bit like physics, so we're considering our high potential areas. We're assuming they're just a point and with no size at all. So that is maybe also too simplistic, particularly when the high potential area becomes quite large. And lastly, we also consider just the energy that a heating source may provide. And that might be too simplistic because it doesn't consider the fact that our heat demand actually changes during the course of the year. So in the winter, we need more heat, so we might have to better look at the maximal heating power that the heating source can provide, not just the heating energy. And that brings me to the end of our talk. Thank you very much for your attention. Do you have any questions?
Thank you, Mirjam and Lin, for this exciting talk. We have time for a few questions. Are there any questions? Okay.
Thank you for the interesting talk. We did a similar calculation at our company because we have a geothermal plant. And what we had to consider was that building the pipes not on the roads is a lot cheaper than building them on the roads. So in your example with Berlin, there was clearly a line over a green area straight to the interesting part where the heating is demanded. Did you consider just putting the pipes there instead of following the roads?
Currently, no. Currently, we're just using the street map or street network and just following the roads. But that would also, I added to the list of extensions.
We have one question there.
Yeah.
Right. Sort of almost the inverse of that question. Are there costs at like crossing a railway line or major road and things like that that you can model?
Yeah, we want to consider that in the next step. So we're currently not considering the different grounds or types of grounds that the path crosses or the shortest path crosses. So what you would actually need is a weight or cost weight for the type of ground that the path takes. And it might be cheaper to just follow the road because that's usually how it's done. But as soon as the road crosses then a railway or river, we actually would want to prohibit that or have a cost penalty in there. That is something that is typically considered, but we currently don't because it is a proof of concept.
Yeah, I'm doing some stuff with electricity power supply, so you don't want to hook up to a substation
certainly.
The other side of a railway line because it costs loads of money to pipe it over the top.
We are aware of the problem, and yeah, it's a challenge to build it because it makes the model more complex. Yeah.
Okay, since we are going into lunch break, I would suggest that you reach out to Mirjam and Lin with your further questions during the lunch break.